Hello everyone, and welcome to the presentation of our paper called Female Y27, Bias Evaluation on Data and Algorithms for Effect Recognition in Faces. I am Jaspar Pahl, and I am speaking on behalf of our team today, including Ines Rieger, Anna Möller, Thomas Wittenberg, and Ute Schmid. Since not everybody might be familiar with the field, we'll first talk about the basics you need to know in order to take the most from this presentation and motivate why this research needs to be done. The first one is effective computing itself. What is that? Effective computing is a research field which attempts to decode human effects using machines. All kinds of sensors are used for detecting human effects, for example EEG, EDA, audio information, and others. However, in this study we are focusing on material recorded using cameras. Humans use their face a lot in expressing their emotions, and cameras are a contact-free sensor and comparably cheap, so they are very attractive for real-world application. In camera-based effective computing, there are different annotation styles which are used to describe what can be seen in a picture. In this study, we will be focusing on two of them, categorical emotions and action units. Categorical emotions like happy, sad, or angry are comparably easy to code because they do not require expert knowledge. They make a direct connection between facial features and an emotion. In contrast, action units do not interpret an internal state of a person, but rather describe visual changes in face. However, coding them requires a special training and is very time-intensive. In the image to the right, you can see a person whose categorical emotion most people would likely describe as happy, and the action units displayed would be, for example, action unit 6, the cheek raiser, and action unit 12, the lip corner puller. In order to automatically annotate such labels, effective computing algorithms usually use some kind of machine learning. However, machine learning algorithms can only learn from what you expose them to during your training process, and tend to have problems with underrepresented cases in their training data. So this is where we start. In order to see how much bias influences the effective computing domain, we post-annotated datasets from the field with missing metadata like age, gender, ethnicity, glasses, and beards. Afterwards, we analyzed the distributions in this training data to answer our first research question. Is there a bias in the metadata of action unit datasets? Then, we evaluate two modern action unit detection algorithms with regard to bias in order to answer our second research question. Are state-of-the-art action unit detection algorithms prone to bias? Finally, we compare the two annotation styles and check if the interpretation-free action unit coding style is less prone to bias than the categorical emotion coding style for our third research question. In order to check if there is bias in the metadata of action unit datasets, we first had to get annotations for the metadata which we can base our evaluations on. As you can see in table number 2 in the paper, only the GFT dataset provides subject-specific information on gender, ethnicity, and age. Other datasets give cumulative information on the distribution or the range of values, or do not give information at all. We used 4 independent annotators to complete the metadata labels and provided the cumulative information given by the dataset publishers to our annotators in order to maximize the quality of the annotations. Since the quality of the annotations has an immense impact on the reliability of the study, we computed Krippendorff's alpha. This is a standard measure for inter-rater agreement which compares the observed disagreement in the labels to the expected disagreement. Its values range between 0 and 1, with 1 being perfect. Values of around 0.8, which we achieved in the combined data, mean good reliability, so we are good to go to use this data. Now we can have a look at the metadata distributions. In figure 1, you can see the number of frames over age of the subjects in the combined data. The color coding are the individual datasets. While the distribution of the individual datasets differ, the vast majority of the combined data is between 20 and 35 years. So yes, there is considerable bias in the data for the age category. Figure 3 plots the number of frames over the other metadata categories ethnicity, glasses, and beards. AA stands for African American, AS for Asian, EA for Euro-American, and O for other. Those classes were chosen based on the annotations of the GFT dataset in order to keep the annotations consistent. The color coding is for gender. As you can see, there is a major imbalance regarding ethnicity, with most of the data showing Euro-Americans. Glasses and beards are within what you would expect. Those annotations are rather important for the second research question when it comes to the algorithm evaluation. Gender is relatively well balanced, with slightly more females. Now, with the first question answered, let's come to the second. Are state-of-the-art action unit detection algorithms prone to bias? In order to answer this question, we first have to pick which algorithms exactly we are going to evaluate. The algorithms in this study were chosen based on performance and how well they are documented in order to make this study as repeatable and comparable as possible. The first algorithm which was chosen is NISL, which was introduced at the 2020 Effective Behavior Analysis in the Wild workshop at the Face and Gesture conference. It produced excellent results in the competition and provides a Git repository for the related code. The second algorithm is OpenFace, an open source toolkit with widespread use even outside the effective computing community. Unfortunately, OpenFace does not give precise information about which data exactly the current version of the algorithm has been trained on. Therefore, we cannot look at their training data distribution. NISL, however, does, which allows us to check if the training data suffers from the same bias which we have already detected in the combined data analysis by answering our first research question. As you can see in the image to the right, the distribution looks very similar to the one we saw earlier, with most of the subjects having a Euro-American appearance. Looking at the data more closely in the left table, one can see that for the underrepresented groups, the gender distribution is highly biased, with, for example, only 14% frames of females within the African American category. Looking at the age, the distribution is also heavily biased towards the age group between 20 and 35, which is what we already saw for the combined dataset in research question 1. Therefore, so far we can say yes, NISL could potentially be affected by bias as it shows strong bias in its training data. It has to be said though, that training data bias is not the only reason why an algorithm can be biased. In order to validate the algorithms, we looked at their general performance regardless of metadata. For the field of action unit detection, the depicted values in F1 score are good, so we can proceed. One example of reasons for algorithmic bias besides training data bias is pre-processing steps. When checking for general performance of the models, we noticed that NISL's image processing pipeline did have problems in the face cropping step. Consequently, images of faces were being dropped before they could even be introduced to the actual action unit detection. This is a problem because we would only be able to measure metadata bias for the easy cases for the face cropper, which is a bias in itself and not what we wanted to measure. This is why we introduce contrary padding, which does not make every failed face detection a negative action unit annotation, but a wrong classification. As you can see in the column marked with CP for contrary padding, this makes the performance drop quite a bit because action units are usually annotated negative way more often than positive. Regarding bias, the interesting observation was that the dropped frames were mostly African Americans in front of a dark background. We assume that this led to problems with contrast values. Now, let's come to the bias evaluations for the algorithm OpenFace. In this table, the number of subjects and frames relates to the numbers in the testing dataset, not the training dataset. Therefore, they cannot be used to make conclusions about the relation between training data bias and algorithmic bias. They rather indicate how reliable the evaluations are. Basically, the more frames you have in a category, the more reliable the numbers. As pointed out earlier, we do not know exactly which data OpenFace was trained on, so we cannot compare training data bias and algorithmic bias. As you can see, there is significant algorithmic bias in OpenFace. The most prominent is in age, where older subjects are significantly more difficult to the point where the algorithm outright fails on seniors. Ethnicity bias is also very strong, with F1 macro being considerably better for African Americans than for Hispanics, for example. The algorithm is slightly better on males than on females, which most likely also influenced the beard category, which shows similar results. Wearing glasses is a problem, which is reasonable since they are partial occlusions. When looking at the other algorithm NISL, the algorithmic bias in ethnicity is smaller and very different from the one we saw in OpenFace. The contrary padding we explained earlier mostly influences the performance for the African American group, which is to be expected considering only roughly half of the faces were detected. Among the other groups with sufficient test samples to be reliable for conclusions, there is not too much of a difference. Notably, both the Asian and the Hispanic group perform better than the Euro-American group, despite having a considerably smaller share in the training data, as we showed earlier. As already said before, there can be many more reasons for algorithmic bias than just training data bias. Looking at the other metadata in NISL's evaluation, here we can see a continuation of the same trend regarding age we saw in OpenFace already. Older persons are considerably harder to annotate correctly, which we can now compare to NISL's training data distribution and see that it is in accordance with the bias we've seen there. Contrary to OpenFace, females are actually analyzed more reliable than males, which is again in accordance with the training data bias. There is virtually no difference regarding beards, and just like in OpenFace, glasses are problematic. Wrapping up for research question 2, yes, we can definitely say there is algorithmic bias, some of which with varying direction depending on the algorithm. We can now come to the last research question, where we compare the different styles of annotation regarding susceptibility to bias. In order to compare both annotation types, we needed a dataset which provides both action unit annotations and categorical emotion annotations at the same time, while not being a training dataset for the algorithm itself. This left us with only the CK+ dataset and NISL algorithm combination. As you can see, the difference in bias for the gender category is very small in both annotation types, so there is basically no difference regarding bias susceptibility between the annotation styles. What is important, and is also consistent with some other studies' findings, is that the action unit annotation style works considerably better overall though. The same effect can be seen in the ethnicity bias evaluation. Bias difference between the annotation styles is very small, while action unit annotation is better in general. Since the CK+ dataset has only a very narrow age distribution, a comparative analysis regarding age bias is not viable and is left out here. So, answer to the last research question: no, there's not a significant difference between action unit coding and categorical emotion coding regarding bias susceptibility. Finally, let's conclude and talk about what should be done in the future in our opinion. The first question was if there is a bias in the metadata of action unit datasets. We can clearly say that there is a significant bias. While individual datasets differ in the direction of the bias, the combination of all available datasets shows a strong bias in age, with most subjects being young adults between 20 and 35, a very strong bias towards a Euro-American appearance of the subjects, and only a very small bias in gender, with more subjects being female. This is also where our paper got its name from. The second research question was if state-of-the-art action unit detection algorithms are prone to bias. Once more we have to answer yes, there is algorithmic bias in them. The strongest and consistent effect is in age, where both algorithms showed problems in elderly people. We had two more findings which are not necessarily related to bias of the action unit detection algorithm itself, but show similar effects. The first is that face cropping algorithms in the pipeline before actual action unit detection showed strong bias for ethnicity with low performance in subjects with dark skin color. The second is that glasses prove to be a problem for action units related to the eye region, most likely due to occlusion. It is debatable if this can be called bias though. The third and last research question was if action unit detection is less prone to bias than the detection of categorical emotions. The answer is no, but action unit detection is better overall. Finally, we would like to set a few impulses which we think are important. To start, in this study we have seen that metadata distributions in training datasets for effective computing are heavily biased, and the effects actually show in the algorithms trained on those datasets. Most algorithmic evaluations in the field of effective computing only provide average information on performance and do not evaluate for individual groups. This allows for major evaluation oversights in the performance of subgroups and should be changed. In order to make this possible, we have to start working at the dataset level. Most current datasets lack precise information on individual subject meta-information we have used in the study, like age, gender, or ethnicity. Future datasets should contain this information in order to enable research in this field. After better investigation of algorithms and what is required to achieve this, the last point is about how to actually prevent bias in effective computing algorithms. One key point is that active debiasing of datasets as well as algorithms is a necessity for their fair real-world application. Unfortunately, this field is only getting comparably small attention in development while having massive implications for users. This is it. Thank you so much for your time. You are very welcome to ask questions or discuss, either live or just send a mail to my address on the screen in case you cannot make it to the live presentation.